Let's talk about other combination models we can have with ensemble methods. So the first one is the mixture of experts, where we have an ensemble of classifiers, for example, that are specialized on certain aspect of the problem. And the idea is that they are working in parallel, but we have a routing function that is weighting the decisions according to their expertise. So usually we proceed with some kind of weighted voting. The difference is that the weight is based on the X. So here we have this WJ X, which is not a constant here, but a function. And that function will vary according to the expertise of model J on sample X. So this idea of specializing the models on different regions allow to reduce the space correlation, and we can have very different behavior according to the different regions. And we can use simpler models in each region that is capturing really what is going on in that region without necessarily being forced or being trained to fit over all the different aspects of the problem, where we'll see the patterns may be quite different in terms of learning them with the individual models making the ensemble. This kind of approach aims at somehow generating bias but negatively correlated experts. So they might be quite poor outside their expertise area, but can be quite well performing in their own area. So we can expect that maybe there will be some bias in general over all the samples, but that's okay because the weighting would somehow be reduced in the areas where they don't have necessarily the capacity to perform well. So overall, it implies a reduction of the variance, and so the error will be somehow lower because we are able to take I would say, a good bias variance trade-off in terms of processing. And the routing function doesn't have to be linear. It can be nonlinear, for example, using a multi-layer perceptron. That's something that is commonly used to determine the expertise, the weight to assign to a classifier for a given sample. So, but there is a risk that we may increase the variance having some overfit with such a model because we kind of separate in small regions, and each specialization models may be quite fitted to the training set in that region. So it looks like that. So basically, it's really close to the weighted voting with this kind of individual models here that are making decision in parallel according to the input, with the difference of the gating here that is using the X as input and that is determining the weight to use, and this weighting is dynamic. So this is where things are different. We are really dynamically adjusting the weight to give to each member for making the ensemble decision here. Another approach is the cascading classifiers, where we have a sequence of basic classifier that we are applying. And then the idea is that we move from one stage to another only if the confidence of a classifier at one stage is lower than a threshold. And so as such, we just go from one stage to another, and we only make the decision based on the stage where the confidence is high enough to say, okay, we have a good enough confidence here based on the classifier at the current stage, and we use that decision from the classifiers as the ensemble decision. Otherwise, we move forward, we move to the next stage until we reach a stage where we have a good enough confidence, or we reach the last stage of the model. So this confidence can basically correspond to the posterior probability of the classifier at that point. And the thresholds usually are high at the first stages. So the idea is that we may want to have simple models requiring a high confidence threshold to be used. So basically, we will kind of accept only the easy decisions at the first stages. And the harder decisions, the harder samples are processed in later stages. We go deeper in the cascade to reach the point where we get maybe a more complex model that is able to deal with such difficult data or such special case. So for the training, basically what we do is that we train a classifier with the full data set to start with. And we just set some kind of high confidence threshold, and every samples that are rejected at that first stage are used to train the next stage. So basically, we just create the data set xj+1 from the rejections of a previous stage to train the classifier hj plus 1, and so on. We just kind of move on in the cascade until we reach a point where maybe we have too few samples to continue, and the network is big enough, is maybe specialized enough to be able to process the hard cases. So the idea is to start with simple, inexpensive classifiers and go on with more complex, expensive classifiers at a later stage. And such an approach is making sense when we want to do some kind of real-time processing. So as such, we want to not waste too much computation with the biggest models. For most of the cases, we are able to reduce the computational burden and maybe have some kind of really real-time capacity to process most of the samples with the easy models and keep some of the capacity for the harder cases in a way that is keeping the processing to be steady and not lagging behind what's going on right now in our case, in the setting we are working with. So the cascade looks like that. So basically we have the sample here, which go with the first stage, first model. Is it with good confidence? Yes, we stop there. Otherwise, we go with the second stage. We test at the second stage. Is the confidence good enough? Yes, we keep it there. If no, we go down until we reach eventually the last stage. If we always have a too low confidence at all stages, we get the last stage and then we just make the decision based on that classifier because we don't have any further stages. So this is how it is going on in that model. There is another approach called overproduction and selection. In that case, we are making use of meta classifiers. So we can see that each classifier making the ensemble can be seen as a feature. So we have F, or H bar, which is the meta classifier. And the idea is that we kind of generate many of those. So it's like to say we have access to many features for a given problem. So we want more than less features. So here the idea is that we want more than less classifiers. So and then we generate a lot of those, possibly with like things like random subspaces. So we are able to generate a variety of classifiers with this approach. And then we want to pick only a subset of this. So basically we can think about an approach where we generate 1,000 different models for a given training set with random subspace bagging, whatever. And then we will choose a subset of 10 over these 500 or 20 over these 500 models or 1,000 models to make a more efficient ensemble with really a set of models that are choose to be working together and possibility are complementary or at least diverse in many ways. So the idea is to kind of use things like approaches we are using in feature subset selection, which will be presented later on during the presentation in 2 weeks from now, 2-3 weeks from now, we will talk about that. But the idea is simple, is we just use this kind of heuristics, greedy heuristics that will use things like, let's pick one model from the set of models we produce as base classifier, the one that is performing the best first, and then we take the second best when added to the first one as an ensemble that is performing the best. And then let's pick the third one over the pool of models we have and choose the one that will be when joined with the two first, providing us the best performance, and so on until we build the set of the size we want. This is the forward selection approach. The backward is the opposite. We just use the full pool of classifiers and we remove the ones that are the least useful from the pool until we reach the size we want to keep. And we can even have this kind of multi-objective evolutionary algorithms, which are beyond the scope of the presentation, but that are basically making this selection that are maybe reducing the size of the final ensemble while improving the diversity and performance and so on. So we can have many objectives to build this set of models, making the ensemble from a bigger pool of candidate classifiers that we generated beforehand.